Good morning to one and all. Due to some network problem in my location, I am unable to take the classes online. Sorry for that. In this video, we are going to discuss about fifth unit, that is state variable analysis and concept of state variables. I am going to explain each and every topic. Don't worry about the syllabus, just concentrate on the concept. Now we are going to start the subject. State variable analysis, also known as state space analysis. It is an excellent technique or excellent method for design and analysis of control system. Up to now, in previous units, we considered transfer function technique for design and analysis of control system. Now we are saying state space analysis is an excellent technique. Then what about transfer function technique? It's not an excellent technique. It also an excellent technique, but we are having some drawbacks while using the transfer function technique. Now we are going to discuss about what are the drawbacks of transfer function technique or transfer function approach, and what are the advantages of state space analysis while design and analysis of control system. Disadvantages of transfer function approach. In that, first one is transfer function is defined at zero initial conditions. I think everyone know what is transfer function. Transfer function, it is the ratio of Laplace transform of output to the Laplace transform of input by considering initial conditions are negligible. Means by using the transfer function technique, we can design and we can analyze the system by considering initial conditions are negligible. That is one of the major disadvantages by using transfer function approach. And coming to second one, second drawback of transfer function approach is transfer function approach can be applied only to linear time invariant systems. In this, we know what is linear system and what is time invariant system. Linear system is nothing but the system which satisfies the homogeneity and superposition principles. Those systems are called linear systems. And coming to time invariant systems, the systems in which the input and output is independent of time, that is nothing but time invariant systems. Transfer function can be applicable only to linear time invariant systems. Coming to third disadvantage, it cannot be applied to MIMO systems. MIMO systems are nothing but multiple input and multiple output system. Transfer function approach cannot be applicable to multiple input and multiple output systems. It can be applicable to only single input and single output systems. That is third disadvantage by using transfer function approach. And fourth one is it does not give any idea about internal state of the system. Now what is the meaning of internal state? The meaning of internal state is which type of controller and which type of compensators we are using in a control system. It does not give the any idea about the internal state. That is, transfer function approach can give the idea about input and output relations. It does not give the internal state of the system. That is one of the drawback. And coming to fifth one, it is very difficult to perform the transfer function analysis on computers. These are the major disadvantages by using transfer function approach. Now, By using state space analysis, we can overcome all these disadvantages. Okay, now coming to advantages of state space approach. In that, first one is it can be applied to nonlinear systems, and second one is it can be applied to time invariant systems, and third one is it can be applied to multiple input and multiple output systems, and fourth one is it gives the idea about the internal state of the system, means it gives the which type of controller and which type of compensators we are going to use in the control system. And next one is it is very easy to perform transfer function analysis on computers. These are the advantages by using the state space analysis. That's why we are considering state space analysis is an excellent method for design and analysis of control systems. Now we are going to discuss about basic definitions which we are going to use in 5th unit. In that, first one is state. State is nothing but the behavior of the system at time t is equal to 0 by using the previous knowledge of the system. What is the meaning of previous knowledge of the system? Previous knowledge of the system is nothing but behavior of the system at initial conditions. In transfer function approach, we are neglecting the behavior of the system at initial conditions. But in this unit, that is state space analysis, we are going to consider the behavior of the system at initial conditions also. That's the advantage of state space analysis. And second definition is state variable. State variables are nothing but for defining the state. For defining the behavior of state, we require some variables. Those are nothing but state variables. And coming to third one, state vector. That is the state variables. The state variables can be represented by using one vector, that is nothing but state vector. And coming to fourth one, that is state space. In this, the space can be represented by using n number of axes, that is nothing but state space. These are the basic definitions we require in 5th unit. State. It refers to smallest set of variables whose knowledge at time t is equal to 0 together with the knowledge of the input for time t is greater than or equal to t0 gives the complete knowledge of the behavior of the system at any time t greater than or equal to 0. That is nothing but it gives the behavior of the system at time t is equal to 0 by using the behavior of the system at initial conditions. And second one is the state variable or state variables. State variables refers to the smallest set of variables which help to determine the state of the dynamic system. That is, some variables required to define the state, that is nothing but state variables. Generally, state variables are defined by n number of variables, that is x1 of t, x2 of t up to so on xn of t. Generally, in electrical circuits, we consider the number of energy storage elements are the state variables in the state space analysis. That is, energy storage elements in electrical circuits are nothing but inductor and capacitor. Inductor stores the energy in magnetic field and capacitor stores the energy in the form of electrostatic field. The current flowing through inductor is considered as one state variable. Similarly, the voltage across the capacitor is considered as a second state variable in electrical circuits. And next one is the state vector. we already know that is the state variables can be represented in one vector, that is nothing but state vector. That is there is a requirement of n state variables in which in order to describe the complete behavior of given system, then these n state variables are considered to be n components of vector, that is nothing but state vector. Such a vector is known as state vector. And fourth one is the state space. It refers to the n dimensional space which has n number of axes. These are the basic definitions. Now consider derivation of state space equations. State space equations are nothing but equations which determines the behavior of system. State space equations are of two types. The first one is the state equation and second one is the output equation. For deriving the state space equations, consider the following parameters. That is, consider linear time variant system which is having multiple inputs and multiple outputs, and consider R be the number of inputs and M be the number of outputs. That is, R is nothing but input, those are U1, U2, U3 up to so on UR. Similarly, M number of outputs, that is Y1, Y2 up to so on Ym. And consider there are n number of state variables for representing the system. Those are x1, x2, x3 up to so on x. This is a simple block diagram of state space model. Okay, this is the system which is having r number of inputs, m number of outputs and n number of state variables. Okay, modified block diagram of state space model. This is the modified block diagram of state space model which is having e of t is the input and y of t is the output, and here x dot of t is the state model and x of t is the state variable. Okay, state model equations can be obtained, okay, at two summing points, that is summing point 1 and summing point 2. At this summing point we are going to get the state equation. Here state equation x dot of t is the summation of input with some gain as well as state variable with some feedback path gain. Similarly, at this summing point we can get the output equation y of t. Y of t is the summation of state variable with some forward path gain as an input with some forward path gain d of t. Okay, at these two summing points, that is at summing point 1 we are going to get the state equation, at summing point 2 we are going to get the output equation. In that is, the state model is given by the state equation as well as output equation. State equation x dot of t is equal to a into x of t plus b into e of t. Similarly, the output y of t is equal to some c into x of t plus d into e of t. These are the state model equations. In this, a, b, c, d are the matrices which are given by a is the state matrix. The size of A is n by n. Similarly, B is the input matrix. B is the input matrix of size n by r. Similarly, C is the output matrix. The size of the output matrix is m by n. Similarly, D is the transmission matrix, also known as direct transmission matrix. The size of the transmission matrix is m by r. And where x of t is known as state vector of size n cross 1, n by 1. Similarly, y of t is the output vector of size m by 1. E of t is the input vector of size r by 1. Now we are going to discuss some basic problems on state space model, that is obtaining the state equation as well as output equations for some electrical networks as well as for some transfer functions. In that, first one is obtain the state model for a given electrical system. Okay, this is our electrical system. Okay, for obtaining the state equation as well as output equation for this electrical system, okay, first point is we have to determine the number of state variables. Okay, number of state variables represents the number of energy storage elements in a given electrical system. Okay, this is simple series RLC network. Okay, the number of energy storage elements are inductor as well as capacitor. So for this electrical network we are having two state variables. Consider those two state variables are current flowing through inductor, that is I of t. Similarly, voltage across capacitor, that is V naught of t, are the state variables. Here V I of t is the input and V naught of t is the output. Okay, that is there are two energy storage elements, that is inductor and capacitor. So number of state variables are 2, current flowing through inductor, that is I of t, and voltage across capacitor, that is Vc of t. Okay, from the circuit the output voltage is nothing but the voltage across capacitor. So V naught of t is equal to voltage across capacitor Vc of t. Just apply KVL to the loop. By applying the KVL, we will get this equation, that is input is equal to voltage drop across resistor, that is nothing but R into I of t, and voltage drop across inductor, that is L into di of t by dt. Similarly, voltage across capacitor. Okay, from that find out the di of t by dt. For finding di of t by dt, just divide entire equation by L for eliminating this one, and consider the all the terms towards the input. So we are getting di of t by dt is equal to this equation. And here I of t is one state variable and Vc of t is the another state variable and Vi of t is the input. Consider this is one equation. Similarly, the voltage across capacitor is nothing but Vc of t is equal to, we know formula, that is 1 by c into integral I of t into dt. Okay, for obtaining the state variable, state vector, differentiate this one with respect to t. So we will get dVc of t by dt is equal to I of t by c. We can eliminate the integrator. Okay. From that, state vector x is nothing but two state variables, I of t, that is nothing but x1 of t, and Vc of t, that is nothing but x2 of t. And from that the differential state vector is nothing but x dot of t. Okay, x dot of t is nothing but just to differentiate these two. So we are getting di of t by dt and vc of t by dt. Now by using above equations from the state vector, state equation as well as output equation. That is, state equation is nothing but a into x of t plus b into u of t. Okay, from first equation, okay, that is, this is the matrix A and this is the matrix B. Similarly, from the output equation, that is vc of t, we are getting this thing, y is equal to 0 into 1, 0 1, matrix 0 1 and matrix I of t into vc of t. Okay, by comparing all those things, we are getting matrix A, B, C, D, and these two are the state model for a given electrical system. In some cases, we have to find out the state space model from a transfer function. Okay, now we are going to obtaining the state space model for a simple transfer function. That is, consider given example. Find the state space model for the system having the transfer function, that is y of s by u of s is equal to this one. Here y of s is the output and u of s is the input. Okay, before obtaining the state space model, just cross multiply the given transfer function. By cross multiplying the given transfer function, we are getting this one, that is s square plus s plus 1 into y of s is equal to u of s. I think everyone know inverse Laplace transform of y of s is equal to y of t. Similarly, inverse Laplace transform of s into y of s is equal to dy of t by dt. Similarly, inverse Laplace transform of s square into y of s is nothing but d square y of t by dt. So for this equation, apply inverse Laplace transform. By applying the inverse Laplace transform, we are getting this equation by knowing these formulas. That is s square into y of s. Inverse Laplace transform of s square into y of s is nothing but d square y of t by dt square plus s into y of s is nothing but this one, plus 1 into y of s is nothing but y of t, that is equal to inverse Laplace transform e of s is equal to e of t. For this, we have to obtain the state model. For obtaining state model, first consider y of t is equal to some state variable x1 of t. Okay. Further consider differentiation of y of t. Differentiation of y of t, dy of t by dt is equal to differentiation of x1. That is nothing but x1 dot, that is equal to consider one more state variable x2. By substituting all the state variables in this equation, we are going to get this equation, that is d square y of t by dt square is nothing but x3 plus this one is x2 and y of t is nothing but x1, that is equal to input e of t. Okay, we can simplify this one, we will get this one. Here x3 is nothing but x2 dot, so in place of x3 substitute x2 dot, then we are getting this equation. Similarly, we know x1 of dot is nothing but x2 and output equation y is nothing but x1. Okay, by using x1 of x1 dot as well as x2 dot, we are going to get the state equation, that is nothing but x dot is equal to a into x of t plus b into u of t, and by using this output equation, we are going to get the output equation of the state model, that is nothing but that is state equation is, this is x2 equation, and x1 dot is equal to, we know, x2, and the output equation y of t is equal to x1. Okay, by using x2 dot equation and x1 dot equation and y of t equation, we are going to form the state model for a given transfer function. That is, x dot is equal to matrix x1 dot, x2 dot is equal to, this is the matrix A, and this is matrix B, and this is matrix C, and coming to matrix D, that becomes 0. Why? Because here there is no input term. So this is the state model for a given transfer function. In the next video, we are going to derive the expression for transfer function for a state space model. Thank you.